Hello. Pull. Oh. Ooh. Yeah. Woohoo!
The more radiation it emits. Some of it even becomes visible light that we can see. Infrared radiation is a type of electromagnetic radiation which has a lower frequency than light and involves waves rather than particles. This means that, unlike conduction and convection, radiation can even pass through the vacuum of space. This is why we can still feel the heat from the sun even though it's 150 million kilometers away from the Earth. Some surfaces are better than others at emitting and absorbing infrared radiation. Dark matte surfaces are good at emitting and absorbing infrared radiation, which is why solar panels are black in order to absorb the maximum amount of heat for your hot shower. White, light, shiny surfaces are poor at absorbing and emitting infrared radiation, but they are good reflectors, which is how a thermos works. If you want to keep your cup of tea hot all day, you put it in a thermos that is coated inside with a shiny surface to reflect the radiation back to the tea and keep it warm for hours.
We showed that the net radiative heat transfer from or to an opaque diffuse gray surface, Q sub I, is equal to the area of that surface, J sub I minus G sub I. J is our radiosity, which is all the radiation that leaves the surface, and our G is our irradiation, which is the radiation that's incident on the surface. For an opaque diffuse gray surface, our radiosity is equal to the emissive power plus the reflective irradiation, since that's the only part of G that leaves the surface. Let's put this in a more useful form and use some of the things that we know about this type of surface. The first thing is that our reflectivity is equal to 1 minus our absorptivity, since there is no transmittance. According to Kirchhoff's law, 1 minus epsilon, or the emissivity. We can also write the emissive power as the emissivity times the emissive power of a black body. So now let's rewrite our radiosity. So we're going to write that irradiation in terms of the radiosity. Now we're going to go back to our original equation right here and substitute in our irradiation. So let's do a little algebra here. And finally, we can simplify this to our emissive power of the black body minus the radiosity divided by 1 minus the emissivity divided by the area of the surface times the emissivity. And the reason we put this in this form is we can look at it as this is the driving force and this is the resistance. And using this, we can look at the radiative heat transfer from one surface to a number of different surfaces in an enclosure, which I'll show you in a subsequent screencast.